Hello, it's Martin here with some S3 work. Today we're going to look at goodness of fit and chi-squared distribution. So objective here is to apply a goodness of fit test for a discrete uniform distribution. So what exactly is that? Well, a goodness of fit test, it measures how well observed data, so data you've collected from an experiment, how well that data fits a known distribution. So see if you can find a suitable model for that data. One distribution we met in S1 is discrete uniform distribution. Okay, there's plenty of other types we can apply goodness fit tests for different types of distribution, but for this video we're just going to look at discrete uniform. So just a reminder what that is. This is where the probability for each variable is equally likely. So for example, when you roll a die, you've got just as much chance of getting a 1 as you have a 2. Okay, so you expect the probability to be the same for all the variables. So in our example, we're going to take some data from an experiment and we're going to see if it fits a discrete uniform distribution model. Now, we've got quite an unorthodox example here. Now, there's a program on Sky 1 called Ducks Don't Quack Echo. What happens is celebrities come on and have very sort of bizarre questions, hypotheses if you will, and then they test those hypotheses and then they comment on the data at the end. So a bit like what we're going to do here. Now, we have quite a peculiar example here. One of the celebrities came on the show and asked, when you go to the toilet, which cubicle do you choose? They were concerned that some cubicles were more likely to be selected by members of the public, meaning they would be not as hygienic. So what we need to do is we need to work out what our null hypothesis is and the alternative hypothesis, so H0 and H1 retrospectively. Now, we first met hypothesis testing in S2, and this is you're innocent till proven guilty, basically. Okay, so in the courtroom, the defendant is innocent, H0, unless evidence suggests otherwise, to reject the null hypothesis and accept the alternative hypothesis. So we need to work out what that means for our example. Well, H0, well, that's each cubicle has an equal chance of getting selected. And then there's H1, which is there is not an equal chance of each cubicle being selected. So basically, if there's an equal chance of each cubicle being selected, then this data will fit a uniform discrete distribution model. Okay, so therefore we'd have to accept H0. If we find that it doesn't fit that model, then we accept H1. We're going to test this at the 5% significance level. So we need to be at least 95% certain, okay? Or, in other words, at most we're going to give ourselves a 5% chance of being wrong. Okay, typically when you do a lot of hypothesis testing, 5% significance level is a common level to use, but we can use other levels as well. Now don't worry, we're not actually going to do this experiment. And we've got our data already. So our data, they observed 150 people outside 5 cubicles, just to stress. The cameras were on the outside, not inside. So here's our doors. Okay, we've got the entrance there at the left, and doors 1 to 5. So if H0 is true, we expect 30 people to go to each cubicle. So you expect 30 to go in 1, 30 to go in 2, etc. That's because if we got 150 results and there's 5 doors, 150 divided by 5 is 30. So we'd expect 30 people to go to each door if our null hypothesis is true, that it's equally likely, people are equally likely to go to each door. Okay. Now we'll have to say at this point, there's one assumption we are making, that we're going to say that only one person is allowed in the toilet at one given time. Okay, so that means that eliminates the option of, well, people may not be able to go to door number 2 because it's already occupied. So that's just one little assumption we're making with this experiment. So the data was collected, and here's our results. Okay, so we need to introduce a little bit of notation here, and you can see here we've got OI for observed data. Each OI represents the number of observations at each door. So O1 would equal 12, meaning 12 people went into door number 1. And O5 would equal 24, meaning 24 people went into door number 5. So to measure the goodness of fit, we use the following formula that you can see down here, okay? And this, what looks like an X, this is uppercase chi. Okay, so this is chi squared, and this is what we're finding out. There's no need to square root at the end, we just call it chi squared so we can show this always positive. What goodness of fit is concerned with is it's looking at the difference between your observed data and the expected data. So if you look at the formula there, the more far apart our observed data is from what we expect, the bigger this capital chi squared is going to be. Okay, so the closer this is to 0, the better it fits the data. The more, okay, not so good. So we talked about that we expected 30 people to go to each door. So here's our table updated with an extra row now. Now, one thing we have to take into consideration here is that if any of the expected values fall below 5, we must group together the frequencies. Okay, like anything with stats, if we're working with only a small amount of data, it's not really good enough. We need to have our expected values to be over 5 to do goodness of fit. Okay, so if that was the case, then you'd have to group that together with another variable, just add the frequencies together. So we need to work out our goodness of fit, as we can see here. So we need to work this out. So let's start by taking away the expected value from the observed value for each door. So we do 12 take away 30, 36 take away 30, etc. And I get the following. Okay, so this is just working the top part of the fraction. We haven't squared it yet. Just working out the difference between the observed data and the expected data. And as you can see, on top of that fraction, we have to square that. So let's do that. So square the differences. So you square minus 18. So obviously, because you're squaring, you're going to get all positives here. So then we get the following row. If you're not sure how we get that, just have a look at the table and work through the values yourself. And hopefully you get what I've got there. And then we're nearly done. We just now need to divide by the expected value. So we're going to divide 324 by 30. Okay, and we'll do that for all our other values. So we do 36 divided by 30, etc. And then we're on our way to getting our chi squared. Okay, because we have to sum the values together, you have to add that bottom row together. So add the 10.8, the 1.2, etc. and hopefully get 21. So yeah, again, if you're not sure, work through it yourself, okay? And see if you can match up with 21 and just check your values with mine along the way. So now we've got to compare this to the critical value of chi squared. So this is now lower chi. And as mentioned before, we're going to test this at the 5% significance level. So we've done it for observed data. Now we're going to compare it with some theoretical solutions that have already been constructed for us. And in order to do that, we have to use some tables to find these values that have already been worked out for us. What we need to do is we need to find the number of degrees of freedom. Now what we have to do is we take the number of cells, which includes any combining we've done with the data if it's fallen below, the expected values have fallen below 5, which is not a problem in the example we're doing, but just bear that in mind. And we take away the number of constraints. In the case of discrete uniform distribution, there's only one constraint, okay? So the only constraint is that the last frequency is determined by the other frequencies. And that's the case with all discrete uniform distributions. For example, when you roll a die, the first 5 values you get, if you add them up, and you add the 6th value on, it has to add up to the number of rolls altogether. So the last frequency you take is dependent on the other frequencies. Okay, if you've got 103 1 to 5s on a die and you've rolled it 120 times, the last value has to be 17. Okay, it's a constraint. It has to be a number that equals 120 altogether. So, and that's going to be the case with all discrete uniform distributions. You just need to take one away. So we had 5 bits of data, 5 cells. Take one away from that. We have 4 degrees of freedom in our example. Which means we're now ready to find our critical value. So this is what we're trying to find. Chi-squared for 4 degrees of freedom, and we're testing it at the 5% significance level. To find this, we need to use the table. So we need to use these statistical tables, which we have here. Okay, so we have to look here for nu. Okay, so that's this Greek letter that looks like a V. We go down to 4 because remember, we have 4 degrees of freedom. Okay, and then find the probability that we're testing it at. Okay, so 5%, and you can see here, at the 5% significance level, we've got 9.488. Okay, so this means if we want to see if it fits this model, it cannot exceed this 9.488. Okay, we expect sometimes that there is going to be some slight changes from the expected values. Okay, if you flip a coin 100 times, you're not thinking that you expect to get 50 of each. But if you get 51 heads, 49 tails, you accept that as fine, okay? But it gets to a certain point when it gets too far away from your expected results that you have to be suspicious, okay? And we're testing at this 5% significance level, so i.e. 95% certainty. And if we look at our data, well, when we worked out chi-squared for our observed data, we got 21. When we've looked in our table, we get chi-squared to be 9.488, okay? So since 21 is more than the critical value of 9.488, we reject H0. So we reject the null hypothesis that a discrete uniform distribution would be suitable, okay? So because we reject H0, we have to accept H1, that the discrete uniform distribution is not a suitable model. Okay, because of our goodness of fit test. Each door does not have an equal chance of being selected, okay? Because if it doesn't fit this discrete uniform distribution model, it means every door does not have an equal chance of being selected. We've found from, or at least from our observed data, that is what we've found. So would we reject this at the 1% significance level? Let's go back to our table. So our degrees of freedom, we still have 4 degrees of freedom, but this time we're going to go to 1%, and that's 13.277. We're still going to reject H0 because it's still less than 21, okay? Or we can say 21 exceeds that value of 13.277, okay? So even if we want to be 99% certain, okay, that it's not just we've got anomalies in our data, then it still does not look like good for a discrete uniform distribution model, as it exceeds the critical value. Right, well, I've done some talking, so now it's your turn, okay? Here's a problem for you. So I'll read out the problem, then if you want to pause the video, have a go at the problem yourself, and then I'll go through the solution and see if you get what I got. So a die's rolled 240 times, and here's the results. Okay? And you're going to test this at the 5% significance level, whether or not the observed frequencies could be modelled by discrete uniform distribution. Okay, so you've got the data there, and you're going to test that for the 5% significance level, whether or not the observed frequencies could be modelled by discrete uniform distribution. So let's look at the solution. So I'm going to go through this step by step, and the first thing we need to work out is what's our hypotheses. Okay, so what's H0 and what's H1? The null and alternative hypothesis. So H0, well, that's the observed distribution, can be modelled by a discrete uniform distribution. H1 is that it can't be modelled by a discrete uniform distribution. Okay? So really with H0 we're saying that the die isn't biased if we accept H0. If we're accepting H1 we're saying there is some bias with the dice, okay? Because when you roll a die you expect it, if it's not biased, to get the same distribution for each number. So if H0 is true, what's our expected values for each variable? So remember, we're testing discrete uniform, so every expected value's got to be the same. And we've rolled the die 240 times, so if there's an equal chance of getting every single outcome, then you expect to get 41s, you expect to get 42s, etc. So EI is going to be 40. Now we're going to draw out a table to find the following. So this is where hopefully you have something like this, or you've been working through something similar like this. First thing to do is find your differences. So hopefully you should get what I get on that row. So that's just your OI minus EI. But then you have to square it. So we should get the following. And then you have to divide all those values by EI. So you're dividing all those values on that bottom row there by 40, and you get the following. Because you have to find the sum of all those values, just add that bottom row together, and we get 5.25. So this is what we've got from our experiment. So now compare with the critical value of chi-squared. First we need to find our degrees of freedom. So we have 5 degrees of freedom, because remember, when we're dealing with discrete uniform, we lose 1 degree of freedom because of the constraint of having to make sure your last value makes everything add up with the rest. And remember, we're testing at the 5% significance level. Therefore, you need to find chi-squared with 5 degrees of freedom at the 5% significance level, as so. Back to our tables. This time, nu is 5, so find 5, go across to 5%, and you can see it's 11.070. So is this what you found from your chi-squared when you did from your observed data? Is that less than the critical value? Well, 5.25, it's less than 11.070. Hopefully you can see that. So therefore, we do not reject the null hypothesis at the 5% significance level. We have to accept it. So well done if you got the following values and came to that conclusion. If you have any questions, leave in the box below. I've been Martin. Thank you for listening.